Again, welcome to everyone, and thank you for joining us today. We're very excited to be offering this webinar in conjunction with Luke Schenck from Merck. We're going to be discussing the application of high shear mixing, rotor stator technology in particular, and its impact in particle engineering. So what we'll do here is start along, and just to give you a little bit of a quick background on ourselves. Wayne Harwood, I'm the National Sales Manager for the Quadro Liquids Division. I've been with Quadro for about 12 years now, and in a variety of roles, but starting in our technology center and then on into sales applications as well. And then we have Luke Schenck of Merck, the principal scientist in a particle engineering group. We've had the privilege of working with Luke for many years, and we were excited about the opportunity to do this together today. And I would say, kind of without further ado, I'm going to turn things over to Luke. He's going to start off by discussing his work over the last several years, and kind of the progression of how things have evolved over time as well. And then following that up, I will do a kind of a quick introduction into the Quadro HV, just to give a little bit of high level background for you. Then we'll open up to some Q&A at the very end. Luke, I'm going to pass things over to you, and we can jump right in.
All right, let me get the laser pointer back up in case I need it, and make sure I can advance here. And I'm assuming the audio still sounds all right, Wayne and Matt?
Yes, sir.
All right. Now, thanks for the opportunity to present. I think we've had a really fruitful collaboration on the technology and how we've started to implement this at Merck. So I'm happy to talk through some of that today. And I'll go through pretty quickly. I have some references throughout for additional details, and if folks have questions, hopefully there's time at the end for the Q&A. So the agenda, I'd like to go through the motivation for expanded particle size range and particle size using the HV units and wet routes as an alternative to dry milling. I'll give some background on particle size reduction efforts via wet milling and how we've applied the technology at Merck. Evaluate expanded scaling capabilities with the HV product line. From a top-down comminution-based standpoint, then talk about, once we had an improved understanding of the hydrodynamics, how we've applied that to precipitation of micronized API, and then move on to sort of, as these pieces have solidified, how we think about using this for advanced particle engineering, where we have precipitation plus the addition of non-active components to design composite particles. And we'll do this with both crystalline API and amorphous API. So to start with the case for wet milling, when we look at the typical particle size or a portion of the particle size ranges that can be achieved, jet milling features pretty prominently here, or did historically. It's a proven technology. It generally achieves the target size range in the sub 10 micron range, more typically in the, let's say, 2 to 5 micron range. Availability across the network has really been a workhorse, but it has some risks. There's lower productivity and yield. Some compounds can be challenging to jet mill. There are industrial hygiene concerns where you fluidize potent compounds. What does containment look like? It can also result in disorder in the milled materials, either lattice strain, non-uniformities, amorphous formation, and this can be detrimental to stability and downstream processing. So we really have looked to alternatives to dry milling, and one that's featured prominently again is wet milling. So I'll just touch on basic operation and why this has become a favored route. So wet milling really can be implemented pretty easily within conventional crystallization processes, where this can be done almost in the flow of typical crystallization. It's not adding additional labor and overhead or significant time cycle to the crystallization steps. A fairly modest capital addition, and it achieves normalization of crystallization process variability. Right? So we know crystallization processes could be sensitive to fluctuations in temperature, purity profile, operating conditions, mixing. So there's some normal variability in crystal particle size. And this example here, right, is one where coming out of the crystallization process, the material varied between 70 and 180 microns. And after one turnover, so one pass of the entire batch through the wet mill, you can see we're reducing some of that slightly, but by 5 turnovers now, that spread in the product of the crystallization process is reduced significantly, well within the specifications for this compound. So again, it really normalizes that variability of the crystallization processes. And we think about milling, it occurs in 2 regimes where you have this massive fracture, so the particles are fracturing, and then this can be followed by sort of a plateau of the particle size reduction profile. And this can be a portion of the milling performance where you would get attrition or edge chipping, which can be detrimental. So this portion of the curve is more desirable to operate just from a process robustness standpoint, but you don't want to stay here too long, because if you start to generate fines, this can be detrimental to filtration processes, downstream flow, compressibility, etc. And a lot of this is documented. There's some references here that have really good details on these steps. So as we were looking to implement the HV product line, we thought there was an opportunity for an expanded size range that could be achieved through this route, where typically wet milling would get us into that 30 to 50 micron range. With the higher tip speed that we could achieve with the HV line, we were getting into that 15 to 30 micron range. And we wanted to make sure that this could be achieved across a range of material properties. So we looked at blocky materials, high aspect ratio materials, and needle-like materials. And fairly effectively across the board, we saw appreciable particle size reduction and you know, a lower size that could be achieved with the HV product line. So this was really encouraging. And again, this is where great collaboration was in place with Quadro Engineering, where we also thought, well, how could we further reduce the size range that can be achieved here? So we looked at evaluating rotor stator combinations with slightly reduced clearance, and saw we could get even further reduction with both rod-like and blocky materials. So again, a good reduction in the X50, the mean volume, as well as in the X95. So getting us more into like the pin milled particle size range, ability to use wet milling for a broader portion of the pipeline, and even a narrowing of the distribution, right, as we see the X95 being reduced more than the X50. So with right, the opportunities here that we saw with reduced particle size, we wanted to look into collateral benefits of this as well. We'd like to implement the technology more. What about the process robustness or the ability to scale this the HV product line from bench up through pilot and production? So this is an example of a compound that we were wet milling with different equipment. Again, in some of those earlier manuscripts, right, it wasn't uncommon to track particle size reduction as a function of batch turnovers, right? That's the number of times the entire batch has flown through the wet mill. And we leveraged process analytical technology to call the endpoint of milling. So generally, we could hit the target particle size if we had a fixed tip speed, although the kinetics of that particle size reduction weren't always consistent. And that really wasn't a challenge, right? You just have PAT online and call the endpoint of milling. But occasionally, and this is the case here, where even the tip speed had to be changed. So we were milling at production scale. It looked like the particle size started to plateau. So we had to increase tip speed to get us into the target particle size range. We wanted to see, you know, is this something that we would also observe with the HV product line as well? So initially, we thought, what could be some of the sensitivities that would explain discrepancies in scale up? So we thought about the flow rate of the material through the mill, the suspension concentration, the starting particle size. And these are covered in the manuscript as well if folks want to look for additional details, but none of these explain the type of variability that we saw in scaling up with the historical wet milling, which really had us looking more at the mill geometry and how can we think about differences in the design across the product line and our approach to scale up. So when we looked at the HV mills, we evaluated whether geometric consistencies with the HV product line would translate into improved scalability. So could we scale up based on purely geometric considerations? So assuming you'd have a fixed tip speed, the shear that the material would see would be consistent at this fixed tip speed, and then we could just take into consideration again the differences in geometry on scale up and see if we could and take that approach to scale up rather than going into like a CFD analysis of the the shear that the material was experiencing at different scales. We thought about these components of the geometry, the height of the slots, the slot width, the vertical distance between the rotor stator, the horizontal distance between the rotor stator, and the number of slots in the rotor and stator. So the hypothesis here was that the terminal size was dictated by the max stress, which was occurring as the flow transferred from the slot on the rotor to the slot on the stator. We would assume this is fixed at a constant tip speed, so we weren't doing a CFD analysis and scaled just based on sort of the probability of material seeing the highest shear. So again, we lost some animation here, but you can imagine the red line where material would go around the high shear, sort of over the overflight region of the rotor stator, or the green line if it's passing through the slots on the between the rotor stator and seeing that max stress. So we looked at this as sort of a ratio of the area of the slots over total area, which is area of the slots and the area in the vertical distance between the rotor and stator. So we were calling this a slot event, which is sort of the frequency and probability of material passing through again those slots and where material would experience the highest shear, which again would dictate that terminal particle size. And again, we lost a bit of animation here, but so we ran on the bench scale and generated a particle size reduction as a function of batch turnovers, predicted what this would look like based on that slot probability approach, and saw in reality that this matched quite closely. And there's a couple other compounds in the reference here to show the application of this. As well as some additional approaches we took where we changed the number of slots, both more and less. We changed the height of the slots. We even scaled this down to a custom HV mini. This wasn't in the manuscript here, but found that this slot event model held across these cases. So again, we could take an approach to scaling just based on the geometry, and this sort of proved to ourselves that yeah, this max shear that the material is experiencing between scales is consistent. Given we fixed that tip speed, and that wasn't true of some of the other wet milling equipment that we looked at in the past. So with more confidence in scale up, we looked at how might this translate to bottom up precipitation, right? If we can control the mixing, can we get into that sub 5 micron range? And we looked at, in this case, this high shear direct precipitation, and saw that we could get into that similar size range as a spiral jet milled, arguably with a slightly broader distribution, but we were getting pretty close considering this was one of our initial attempts. This worked with another compound as well, again, getting us into that like sub 5 micron range, which is where previously we would have looked to jet mill. And this is a more recent manuscript where we thought, well, once we could sort of engineer material into this micronized size range through different routes, right, which could be a dry milling route or direct precipitation, what might differ between these materials? Right, so we're hitting our target particle size in all cases, but does the mode by which we get to that micronized size range influence the crystal surfaces, right? Which faces are we preferentially exposing in these micronized materials? Are there different functional groups on those faces? And how does that translate to things like cohesive adhesive balance, how the API particles adhere to themselves, how it adheres to excipients, which you can imagine could translate into differences in blend uniformity, compression, intrinsic dissolution rate, if those functional group changes could change the hydrophilicity of the resulting material. So in this case, we directly precipitated material from two different solvent systems. We changed the morphology of the starting material, and this is the same form, it's just different morphology. And thinking by shifting morphology, are we changing the preferred mechanical fracture plane, right? Is it going to break on that long axis, or would it break on a different axis that's dictated by the attachment energy in the crystal lattice? And a high level here, again, I'll just show some of this data where we were looking at dissolution kinetics and the blend uniformity of the resulting materials. And it was a precipitated material that had sort of the best combination of properties beyond just particle size. So more sort of a motivation to go with a bottom-up precipitation-based process rather than a top-down jet milling process, just from a standpoint of the material properties. And expanding that a little bit, was another example, and this will start to get into that, like, advanced particle engineering concepts, where here was a case where we had a crystalline material. It had a really nice particle size and morphology. Actually, the growth kinetics were really favorable if you wanted to make large materials. Unfortunately, we wanted small materials to get the in vivo exposure that we were looking for. We could get to that sub 10 micron range through jet milling, but the problem was that resulted in a lot of amorphous formation, which had some liabilities for downstream. So we looked at a direct precipitation using that same approach that we'd found effective for a number of compounds. In this case, we'd make these 25 to 30 micron composite aggregates, if you will, which wasn't within the target size range. So we added, in this case, a bit of polymer and did the direct precipitation, and then we're generating these really nice monomodal particles in the target size range. So sort of a combination of that mixing approach with the addition of this additive mediated crystallization approach to hit our target particle size. So right at this point, you could sort of see the evolution of the technology here. We often need particle size reduction for our crystalline materials. We wanted to move away from jet milling, saw some opportunities with wet milling, worked with Quadro to see how low can we get the size from that comminution-based wet milling approach. And we're encouraged by where we could move from conventional wet milling technologies. Saw some improved scaling capability with the technology, and thought with the improved understanding of hydrodynamics, could we use this for direct precipitation, which we did, and found that it worked pretty effectively, and also saw that we can further sort of modulate the particle size coming out of those precipitation-based processes with the addition of other components during the precipitation process. And at this point, we were thinking, well, how fast is this mixing, and how else could we use this as a process intensification step, right, to run chemistry, or to think about precipitating maybe not crystalline materials, but kinetic phases or unstable phases of our API, where we knew we would need really rapid mixing, and we wanted to evaluate that a bit. And I won't go into the technical details here, but the way we approached this was the fourth-born reaction system. So you have a very fast reaction, an acid-base reaction, again, very, very rapid, and then a slower reaction where you have the acid-catalyzed degradation of DMP into methanol and acetone. So you can run this reaction, track how much of the undesirable, if you will, the undesirable product is present, and get an idea of what the mixing in the system looks like. So what does that look like? If I run with an excess of my base, with this instantaneous reaction, all of the acid should be consumed, and I won't see any of that undesired product of the acid catalyzed degradation of DMP, this undesired product W. So again, ideal mixing at microscale, I don't see any of the undesirable product. If I have poor mixing at the microscale, I don't consume all of the acid with this instantaneous acid-base reaction. I have some acid present, and then on the time scale of this parallel reaction, I could form the undesired byproduct, which we could track in our product stream and see how good was the mixing. So we looked at this DMP conversion as a function of tip speed, saw that this did work quite well, started to look at DMP conversion as a function of DMP concentration to start to get a read on what is our characteristic mixing time. We didn't take this as far as getting to like Damkohler number or definitive read on the characteristic mixing time, but we saw enough at this point, right, that the mixing is quite fast, and you can look at some of the mixing literature with this to gauge like where does this fit compared to impinging jets or static mixers in terms of the type of mixing that can be achieved. So again, the mixing here is quite fast. And this really led to then the next phase of the work with, okay, we know we can use the equipment for top-down milling. Can we use it for bottom-up precipitation of crystalline materials, the addition of additives to sort of tune the particle size there? What about something where we need really rapid mixing and the formation of amorphous solid dispersions as an alternative to hot melt extrusion and spray drying? And it's amazing, like back in the 60s, when folks were first looking at amorphous solid dispersions, they were doing it through precipitation-based processes, maybe at more forgiving drug loads or more dilute reaction streams, but that was how it was done. Later on, Roche brought this process forward for a commercial compound where they were using rotor stator devices to do the precipitation. And then at Merck, we started evaluating this for non-ionic polymers into non-aqueous anti-solvents. And really, this has evolved, right, with how do we design, more involved particle architectures? How do we think about making that material for tox studies, expanding the space to accommodate more polymers and APIs, which had properties that might not be amenable to spray drying and hot melt extrusion, and then even thinking about like layering out of other structure in these materials to modulate compaction properties, flow properties, and even dissolution and in vivo performance. And again, I won't go into a lot of the details here. Some of them are highlighted in the manuscripts referenced, and some of this work is still pending. But really, this sort of idea of this really rapid mixing, allowing us to precipitate molecularly uniform amorphous glasses that then we can have other excipients present that have a function during the isolation steps to have this like composite architecture that has rather desirable properties downstream. And again, some details. This is from our initial work. Again, it's we're precipitating amorphous material that's X-ray amorphous, a single TG through DSC. The dissolution is on par with spray dry material, and then in a canine PK model, the exposure was also in line with what we saw through spray drying. And then the next step, right, we looked to isolate some of these materials through the thin film evaporation process. Saw if we filtered and dried those materials versus if we process those materials in the thin film evaporator, we can get improvements in bulk density, improvements in flow metrics for this, and rather favorable compaction profiles compared to spray dry materials. So again, sort of building on that approach to how do we use this technology, where does this fit into a broader process train to design the ideal, most ideal product. And in this case, again, further modulation of the bulk powder properties through the isolation step. What this translates to is with the good compressibility, we don't need a lot of additional excipients. We can form a rather high drug load composite particle. So here we're, with spray drying, we need roller compaction, we need additional excipients, and we can get about 100 mgs of API into a 1,000 mg tablet. Whereas with the material through this process, right, we have twice the amount of API in a smaller tablet, which is desirable from a dosage unit burden and patient compliance standpoint. And we found that the material was equivalent in a dog PK study. Yeah, this work is pending, where again, thinking about this particle architecture and adding additional excipients that then coat the precipitated material and seeing some favorable results in terms of a dissolution and PK performance of this and our ability to further push the drug load in these amorphous solid dispersions. But I'll just touch on that there's additional directions that we hope to take this approach, right? And the Quadro, this HV rotor stator mill features prominently in how we're implementing these particle engineering approaches. And I think with that, okay, sorry. So the conclusions, I think I've touched on these a few times. There's benefits to wet routes for particle size control. The HV rotor stator line, it reduces terminal particle size, has a lot to be desired in terms of the robustness and the ability to scale. Control of hydrodynamics sort of allowed us to use this for a bottom-up precipitation standpoint, both for crystalline materials and amorphous materials, and then using this in conjunction with non-active components and alternatives to how we isolate materials really allows us to design what we think are some pretty slick composite particles. So, and I think with that, I'll turn it back over to Wayne.
Perfect. Thank you, Luke.
Sweet.
All right. So again, many thanks to Luke for taking the time to present his work over his and his team's work over many years here, and how the HV has played a part in that. We're very thankful for that. I'm going to just go through a quick introduction to the HV, the different sizes, kind of really high level stuff, but enough to introduce to those of you who may not be too familiar with it. Some of the various applications that we might see the HV used in. From the very beginning, we focused in around submicron emulsions, homogenization, kind of that cell disruption type work, as well as milling of APIs and different processes. We have other applications too that are maybe more food or cosmetic based applications as well. So it's not strictly a pharmaceutical type machine. It has plenty of use in other industries as well. But relative to our other technologies, that's kind of where we've seen it fit. And part of the reasons why in conventional work or historical rotor stators, in terms of the energy dissipation they can input into a particular product, kind of top out in this kind of 100,000 watts per kilogram range, whereas there was a huge gap to the next technology, which was typically high pressure homogenizers, about a 3 order of magnitude difference. And we were looking for ways to combat that, and really the HV does that. And what it does is allow us to take that 20 meter per second or 25 meter per second energy input, and by increasing up to that 70 meter per second range, we're now able to, and I'm going to get my pointer back here as well, we're now able to take that up to about 5.5 million watts per kilogram energy input into the process, which is, again, it's starting to close that gap between high pressure technology and rotor stator technology. So it enables us to do a lot of things we couldn't previously do. Quick example on emulsions, and I lost some of the animations too, and I did want to offer Luke as well, if you want to go back at some point and review those, we can have a share presentation direct from a desktop, and we can, if it's helpful. This particular slide had some as well, where basically as we're increasing the tip speed, this is applicable to, say, an emulsion type process. So we're looking at the droplet size we can form. We're starting out here in the 20 to 25 meter per second range, and as we increase the impact on the droplet size we can form, you can see we're starting to hit a kind of a diminishing return as we reach that 70 meters per second, kind of a limitation of the technology in terms of how far we can take it. So that's where we've stopped and kind of evolved the HV technology to. When we first built it, we actually started at a maximum of 50 meters per second, and over time we evolved to that 70. And key to some of the points that Luke presented as well is, scale up is a big part of what all of you probably do, and making sure that what we develop on the lab scale is something we can do when it comes to production scale. And obviously you can't replicate a process like this. So we need ways that when you run these things in the lab, we can scale them up. And so part of our focus historically in the industry, a lot of the focus when it comes to rotor stators is around shear rate. And so one of the things that we learned really early on when designing the HV was that shear rate on its own isn't enough for us to evaluate and effectively scale up our rotor stator technology, because it's a one-dimensional aspect in terms of the gap between the plate and the rotor and how that is impacting the droplet. But what it's not taking into account is the flow rate and the path that the material has to take through the tooling as that rotor and stator spin and they're intermeshed. So a quick example here, just demonstrating how the shear rate on its own isn't enough. These basically, the red line being our incoming droplet size, but the green and the blue indicate two different flow rates through the exact same machine operating at the exact same shear rate. And as you can see, we're able to achieve very different results, almost a 40% difference in the D90 relative to those two performance curves. So the only thing we changed again was that flow rate and creating a very different result. So we learned obviously that shear rate can't be considered on its own. We needed to evolve a little bit further and make sure that when we're scaling up the technology, we take into account a number of different factors. Some of which Luke did touch on as well. And these are just really high level: tooling geometry, tip speed, and what we call the slot velocity, which is a metric of the flow rate passing through the individual slots of the rotor and stator. And then obviously Luke and his teams were able to take and build upon that to develop the slot event theory for applications that are more of a solid milling, which, as he talked about, relies on the probability of materials being hit as they pass through the inline high shear rotor stator. And then certainly the processing time and batch turnovers becomes a consideration as well to ensure that we're achieving the probabilities that line up to make sure that we're able to hit that final particle size and predict roughly when you're going to hit that same particle size. And so what that translates to for us is the ability to scale up from our pilot scale or our lab scale, which is our HV, to our pilot at the HV1, all the way up to the what we call full scale production on the HV3. Now, certainly the titles here vary depending on what your process is. For many people, the HV1 may be full production scale, and in some cases, I've seen even the HV0 is production scale. It all depends on where you're at in your evolution and your process and what that dictates and demands. Now, all three have the capability to run for extended periods without issues, so they can all be used for production. And just a highlight of the details on the HVs. The 0 typically runs at the 7.5 horsepower motor, gives us flow rate ranges in the up to about 2.5 gallons per minute. The HV1, obviously a little bit bigger. Now, most of the time on the HV1 and the HV3, we see people use the larger motor because we want to maximize the capacities. So almost always the HV1s are 25 horse and the HV3s are 60 horsepower units, and the varying flow rates that we can achieve with those particular units as well. And I think lastly, I just want to highlight quickly too that the differences in tooling. One of the things we did when we designed the HV was try to simplify the tooling, the rotor and stator combinations that we offer, in part because we found that they really had, varying the slot size in a lot of cases did not have much of an impact. So we were able to fine tune to 3 different sets of tooling that really covered the majority of the applications that we experience with our customers and the need for with the HV. So those 3 toolings, as you can see, we've got our progressive wet milling tooling, which has slot sizes that start a little bit larger on the interior, get progressively smaller as you pass through the stages. Those are great for applications where you're starting with those larger particles, because that needs to pass into the tooling in order to be able to effectively start milling. The tooling we use typically in the API wet milling industry is going to be the fine wet milling tooling, because your particle sizes typically are already smaller than the 0.5 millimeter slots that this particular set starts with and uses throughout the different rows of the teeth. And then we actually have an emulsion set of tooling, wider slots. We see greater performance because of internal turbulence that's generated as the material passes through a wider slot than a finer slot. So typically when we're doing liquid-liquid blending applications, we will use what we've coined as our emulsion tooling. And at a high level, that is the HV. I think we'll open things up to questions, and I will ask Matt if there's been any so far in the chat. And actually, before we do that, Luke, if you did want to jump back to any slides, let me know and I can pull that up.
I'm fine for now, Wayne, thanks.
Okay, perfect. All right, so if you do have any questions, feel free to enter those in the chat and we will ask and try to answer as best we can. And if we run out of time, we'll always answer those after the fact for you as well. So are there any questions right now, Matt?
Sure. Someone just typing, I believe. I'll let you know when that comes through. Okay.
Perfect.
Just a reminder that the chat is at the bottom on the right-hand side. So I have a question that reads, for a small machine, HVO, what is the tip speed?
Thank you, Oleg. With the HV0, the maximum tip speed is also 70 meters per second. That's consistent across the board for the 0, the 1, and the 3. That is the maximum tip speed. Obviously, we run at a different rotational speed on each of the units to achieve that tip speed, but that is what we.
Okay, just a follow-up with that. What is the rotational speed? Just came
Yep, thank you. So for the HV0, the rotational speed to achieve that 70 meters per second is 15,000 RPM on the spindle side.
Okay. Yeah, it's just confirmed at 15,000.
Mm-hmm.
Okay, thank you for that question. There aren't any other questions. Okay, sorry, apologies. Just one's just come through. What does a homogenizer produce, PSD?
That will depend on the application, I would say. Are you looking at specifically related to API wet milling, or we have some comparable results when it comes to like a milk processing application? I don't know, Luke may have some feedback when it comes to an API milling type application. I would say with milk, we're typically in a similar range. We can achieve similar results by running the HV at 70 meters per second to a high pressure homogenizer at about 2,000 to 3,000 psi. Sorry, Luke. You can. I don't know if I interrupted you.
Okay, so we've got some further questions in. Another question, are the rotor stator assemblies on the HV units capable of hydrating and wetting like the ZC units?
Typically, no. They do not create a vacuum effect this similar to the powder dispersion units, and they don't have necessarily the same interface that would allow those powders to be pulled in. There are the odd instances where I've seen it done. You typically would need a discharge pump to be able to make it possible. And really, it's got to be something that's very, very, very easy to disperse to make it even worthwhile.
Okay. So another question, how do you control, minimize heat generated by the mill during operation?
Great question. There's no internal mechanism to control the heat. Typically, we are looking at ways to remove that heat immediately after and or before the mill in the most extreme cases. So either using heat exchange to regulate the temperature downwards just before it's milled, or immediately after to help regulate the continuing process temperature.
Yeah, we found, right, if we're using this for milling, and use the reduced clearance tooling, there can be a bit more heat up. So if you have, temperature dependent solubility or thermal sensitivity, that could be a challenge, right? We'll just pre-cool the batch and recognize we'll have a delta T across the mill. When we're using that in that milling mode, that hasn't been an issue. If you're precipitating material, again, we'll typically use the emulsion tooling for that. We'll see less of a delta T across the mill when we're doing precipitation and with that emulsion-based approach. But again, we'll just pre-cool the material. And the applications we found that delta T has been acceptable from a product quality standpoint.
Yeah, and I would say in some extreme cases too, we've seen end users use like a cooling wrap around the exterior of the housing to help keep the heat sink of the metal of the housings from rising over time. There's not enough surface area there to make an effective cooling jacket of the housing itself to reduce the temperature, but.
Okay, thank you. Question directly for Luke. Shear aided polymorphic transformation are relative common. Any comment or suggestion for scaling up for the case with multiple forms that may coexist when milling?
Shear-induced polymorphs. I can't say that we've run across that one. Yeah, I think I saw that come in from Carla. And sorry, I had your reference in there for scale-up approaches. So I think Carla has was involved in some efforts as well as at BMS. I had Josh Engstrom's manuscript in there as a reference to scale-up that I think was lost in this version. But yeah, we haven't seen shear-induced polymorphs, right? I think if we were trying to directly precipitate and navigate polymorphic space, we would make sure to have a heavy seed bed to make sure we're templating the right phase. And then if they're an anisotropic, just pay added attention to that delta T potential across the mill and make sure we're running it at a safe temperature where we precipitate out the desired form. And then in the case of amorphous dispersions, we have polymer present to stabilize the amorphous phase, but haven't seen shear-induced crystallization in that case, as long as we have, again, the right temperature, right solvent, anti-solvent system, and the right drug load in that amorphous dispersion. But yeah, I think if you sort of push the limits too far on any of those fronts, perhaps you could get some shear-induced nucleation, but I can't speak to any specific examples of that to date.
Okay. Another question. Are there smaller lab scale devices or techniques to predict PSD, smaller than the lab scale mill, something that could be used, for example, for bench scale?
Not currently. I know Luke's looking at me, waiting for an answer for this one as well. It is something that we have on the radar to further investigate. But at this time, there is certainly not something available that can scale effectively to the full limits of the HV.
Yeah. I would love to think we can get to the point where you could look from, crystal structure prediction and an attachment energy or mechanical fracture plane standpoint and predict, right at this shear stress, what would the particle size be? I would think someone could endeavor to do that if they wanted to spend the time on that, right? What we do is tend to have a small scale tool that we could benchmark material against, right? And understand, okay, if we see this breakage in this small assessment, and folks can think about this more pragmatically, right? You could do an acoustic milling, a media milling, a different approach to rotor stator milling at the small scale, and see like what size reduction would I typically see, and then build a data set to know how does that translate to, you know, a larger scale run when I'm running tens of grams on one of the HV units. And one thing from that reference that I had from Merck on scale up is you can run the HV really dilute, and running at that dilute concentration, as long as you don't have temperature dependent solubility, because when you're running more dilute, right, it's a larger percentage of your batch on a weight basis that would dissolve at elevated temperature. But you can run dilute to get a read on how the milling actually performs with the HV. But that's sort of been our approach with, you know, understanding how you're trying to predict how a material might fracture in a wet milling approach with the HV product line. So I hope that makes sense. I know it's maybe not academically very gratifying, but that's sort of our more pragmatic approach to working with really small quantities of material and anticipating what breakage we'll see on the Quadro. And we tend to see that hold. There's been a couple compounds that don't mill very well, but for the most part, we're getting down into that 10 to 15 micron range with these units for our crystalline materials.
Okay, thank you. And if anyone wants follow-up questions or wants to ask additional questions following this session, please submit them via the Quadro Liquids website, and we can pass them via Wayne to cover some of these points. Another question just come in. Are there any margarine manufacturers currently using this technology or related?
Yes, I did see that one. I was just gonna say, we have done some work with specifically like omega infused type margarine products over the years, which has been effective. And I would say it's not a market that we've done a large quantity of work in, but definitely it is an application that we can be of help with.
Okay, thank you. And just additional questions just come in. Are there any oat milk manufacturers currently using these units?
I would say yes, there is absolutely. Beverages have been one of the stronger applications, and in particular oat milk as well has been an application we've done quite a bit with.
Just hold on for a second in case any more questions come in. Otherwise, as I mentioned, if anybody has a question following the session, please feel free to submit that via the website and we'll get back to you as soon as we can. Okay. So there's nothing else come in for the time being. Thank you to everyone for attending today. Thank you to Luke for joining us as our guest speaker. And thank you to Wayne. As I mentioned, we will make a recording of this session available. And, yeah, thank you for everyone for attending today. Thank you. The session will end now.
Thank you, everyone.
Everybody. Yeah.